So I figured I would go through an example of a modulated structure, preparing it in Apex3 and opening it up in JANA2006. So we'll go all the way through once you've collected the frames stage to the initial solution in JANA2006. So I have Apex3 open here. You can fill this out if you want, but a lot of this will be handled in JANA anyways. So we'll go straight to the determine unit cell section. Open up the folder because you've already hopefully collected the frames and dumped them into this folder. And we'll just select the first one and open. Slide that over. I don't know why it doesn't just start like this, but get it so that you have a reasonable range for the dynamic range of the image, so we could see these reflections. And this doesn't look great, but this crystal structure is kind of crappy, so we'll do what we can with it. But these are okay. It's good enough for our purposes here. We'll go to harvest. And our minimum intensity, we'll just go 20, which is pretty typical. It's already knows the folders to go to. The major difference here between doing a normal structure and a modulated structure here, at this stage, I would recommend harvesting a lot of frames so that we get a lot of reflections. So we've collected 22 runs here, that's a lot, and almost 500 frames per run. It looks like you can do all of them, that'll take a long time, but what I'll do is probably, so all the runs, but I'll do 200. And this is going to take a little bit. All right, now that that's done, well, first of all, the main reason for doing that is getting a good view of the reciprocal lattice. If you harvest fewer runs or fewer reflections, you may not actually get the full scope of what you collected. So this is good for modulated structures in particular, but also for twinning, or just getting good statistics on your initial solution of the crystal structure. It won't matter that much because the integration refines that, but for the modulated structures, this is a critical step. So we can look at that. It's the gray group here, so we can go to View Reciprocal Lattice. It'll load that up. And yeah, so this is definitely not all of what I collected. If I harvested all of them, there would be more reflections up here. But I think this will be enough. I just wanted to save myself a little bit of time. And let's quickly go through interpreting this. This is clearly a modulated structure. If you're unfamiliar, what I'm looking at is you have basically a central row of reflections that correspond to the sublattice, like basically what you would normally have if it was three-dimensionally periodic. That's these high intensity peaks here, so I've aligned this row, and these really close spaced ones next to them are called satellite peaks, and that's your indication of a supercell structure or an incommensurate. So off the bat, I can tell this central row, this row, and this row are definitely going to be a part of our sublattice. So that's going to be good to know later. So back to the unit cell determination. I'm going to click index, and we have the gray group. So the first step is not to index all of them unless you want to solve it as a superstructure off the bat, as in a large unit cell. This is for the purpose of, this video is for the purpose of solving them in greater than 3 dimensions. So I'm going to pick the sublattice. And as you saw, the sublattice peaks, or the sublattice reflections, are more intense. So we're going to put a higher threshold for those. So I'm going to set it at 40. Index in these two, we're using the gray group, and we're going to store the unit cell in the gray. We may have to rearrange these later on, but that's okay. Hopefully we get a good sublattice from this threshold. If we use the lower threshold, yeah, of course it'll pick out those satellite peaks. Even this one did, as you can see, 84. That is quite large. But this looks like a reasonable start. We'll see what happens. I'm going to refine once. Okay, I'll accept. And let's look at it. Okay, this is the right Bravi lattice, at least. I don't think the B-axis isn't correct for a few reasons. You wouldn't normally be able to tell at this stage if you didn't know the structure. The B-axis here is actually supposed to be triple this, which you can modify later on here if you want. But we'll see the repercussions of that later. So I'm just going to pretend like I didn't know that this was supposed to be 9 angstroms. So 537.2. Refine, and accept. Go back to the reciprocal lattice. Okay. So you see the B star direction there. The reason this lattice doesn't work so well is basically, if that's supposed to be B, it would ignore these, and it would also ignore these. These would not be accounted for. So you could see why these would just be systematic absences or something and would not be counted, because all B star is going to count is this and this and this, not that or these, anything in between that increment, because this is a reciprocal view of the lattice, of course. So we can either triple that, or we can select some of these reflections and re-index it, which I think we'll do. But before we go there, I'm going to look for twinning. This is a good idea if you suspect your structure could be twinned, or just, even if you don't suspect, just look for it anyway. So I'm going to just rotate around a few axes, and right off the bat I can see indications of twinning. You see these X's here where the reflections are crossing. So there's one, this is probably the dominant domain, the ones where you see the most reflections, and then there's a separate twin domain crossing it that's probably weaker. So that's another thing that's going to be a problem here, but we'll try to handle it. Oh, this is another good view of seeing why B star should actually be 9 angstroms. It's not going to count for these, because it's okay for there to be blank spaces. They could be systematic absences or something, but it's not okay if you're completely ignoring an increment of rows of reflections. So I'm going to handpick some of these. I'm going to handpick the high intensity rows, because we already resolved what the sublattice peaks are. So I'm going to align it like this, and this is both to get the right lattice, but also to get an refined lattice. To to improve the actual cell parameters. So I'm going to select lattice, and actually I'm going to make these reflections a little smaller so it's easier to segregate some of these. And start from here to the next high intensity peak, which looks like that. That looks pretty good, and I'm going to assign it to a different group, the green group. And I'm going to do the same thing here. Looks good. And I'm going to assign that. So that is looking good. Because along A star, yes, we will be missing the satellite peaks, but we're only looking for the sublattice. I'm not sure if it will come up with the 9 angstrom B for this, but let's try it out. So this time I'm going to go to determine unit cell and index the green group, which now shows up there. So green group, and we can lower this because we've already handpicked, we're not selecting the satellite peaks. So I could even lower that more if they are weak reflections, and index them in the green group. Okay, that looks good. Accept, refine, accept, bravi. Okay, so now it comes up with more solutions. There's the hexagonal lattice, which was to be expected depending on the weakness or strength of the reflection. Orthorhombic is also pretty good. So this could be a guess and check where you just try to solve it in each one of these and go through the process. We actually know, though, that this is monoclinic C because there's a slight misalignment of the satellite peaks, well, actually of the sublattice. And even though it kind of shows it here, that doesn't mean that it's not hexagonal, these values not being 90, 90, 120. But that would become apparent later on. So I'm just going to skip that step and go straight to the monoclinic C, especially since it gives a good field of merit. There's a lot of reasons why you could come up with this monoclinic C, most of it being guess and check, but some of it is actually just looking at the reciprocal lattice. So let's just go with this one. And especially in the scaling, you would find that out too. Refine, refine. Yeah, this is a good lattice. We've got our fixed alpha and gamma with our beta that's very close to 90, but not. Accept. Okay, back to the reciprocal lattice. And it'll change a little bit here because we refined some of the detector position and stuff like that. That'll actually correct the reflections positions as well a little bit. But you can always not refine those as well. There's checkboxes for that. So we've got our sublattice picked out. We don't have all of the sublattice because we're missing these rows and everything, but there's a shortcut for that because we know now that the modulation, the direction of these satellite peaks is roughly along A star, apparently, because that's where the close spaced peaks are. We have a modulation in that direction, and that should be it. We can go to RLAT and incommensurate mode, and we can enable incommensurate mode. So this does an interesting transformation where it shows everything in the central position here reflects, well, it has reflections of this lattice, of the sublattice. Everything that is spaced out away from this lattice will be in different positions relative to 0. So it's just a transformation showing the deviation from this lattice, basically. So if I selected the middle here, I have to rotate it a little bit because there's this line here. If we were looking down this line, you wouldn't be able to see those, but you could see the modulation, or those satellite peaks, the groups of satellite peaks. And the reason that this is streaked out like this is either slightly misaligned cell, or it could be the twinning. But we'll select this central area here. Go rotate or select box, and we'll just select that. We'll assign it to a different group, and then we'll go back to the disable incommensurate modes and see where the yellow reflections are. Now it might be hard to see, but for the most part it looks like the yellow reflections were picked out for the sublattice, for the full sublattice. Looks like there's definitely some missing ones, but that could be in part due to this twinning, which we're going to have to handle at this point now, because it's going to be very difficult to navigate if we don't. So align it in such a way where you can pick out the lattices. Alright, so you can see these are our main reflections here, and we have this intersecting satellite peaks from the other twin domain. So I'm going to select box, and I'm going to assign those to the red group to see where they are when we go to the incommensurate mode again. And you'll see why this is important. Select that. You don't have to do this for all of them. That would be a waste of time. Unless you absolutely had to in some scenario. But we can use our lat to our advantage and just handpick a few of them, see where they are. And move on. Let's pick another. Okay, so we're not going to be fans of the red ones. We can also see, we can kind of see the twin domain here split up here pretty well. So yeah, just rotating around and figuring out a good axis for determining where the different twin reflections are. So yeah, you can already see here that the streaking here is mostly due to the twins. So ideally we would want a better constraint on this sublattice and get rid of these, and we can do that pretty quickly here. I'm gonna rotate, because apparently, so this could have been another modulation vector if you didn't figure out that it was a twin domain, but we obviously figured that part out, and we're gonna just try to get rid of that, or get rid of some of them. and see what it looks like. Commensurate back to the normal mode. Still probably some twins. Not as bad though. So clearly that helped quite a bit, because now, I mean, I see those up there, but there's some here and there, but this is much better. So I'm going to assign more reflections to the sublattice. So what are now our yellow group here, and I'm going to move this up. This probably would have been easier if I harvested more reflections too, like if I harvested 400, but this would be slowing down and stuff. So it's something like that, and I'm going to rotate it just so our alignment is good. That looks good. And back to lattice and yellow group. So from here, it's hard to align, kind of. It's a little bit jumpy. Okay. Selection to that group. From here. This is part of the reason why it was hard to see, is that it didn't use these reflections to refine this lattice. So even though this lattice is roughly correct, it's not perfectly right. And we need more data to refine it. So here we go. And it's that one. This one's a little tricky, but it's that one because you can see this intense peak here. It should be in line with. And I'll try to do that on this side too. That selected some that I didn't want. Okay, I'm gonna have to pan over here and realign this a little bit. There. Or make the reflection smaller would help too. That looks good enough. This next row I might skip because there's not enough information, even though it's probably that one. Let's try it. That line looks pretty good. Yeah. Okay. Let's try to refine that now. So back to unit cell determination. And yellow group. So yellow group goes with the green lattice now. I should probably switch that. Just so that the green unit cell goes with the green lattice. That's always a good practice. So I'll just turn off the grays. Reds are turned off. And we'll just go select all of these to green. So just a good way of organizing. Okay, so refine green with green. Fine. And hopefully we'll see what a difference this makes for the for incommensurate mode. Okay, that beta angle definitely changed. Now beta is 91.2. So now we'll go back. So even the slightest change could have a pretty big impact on how it plots in incommensurate mode. So rlat, incommensurate mode. We'll have to zoom in and pan. All right, this is looking pretty good. And now we can get rid of that. So now the refinement has segregated this row out a little better. So what we can do is select all these central spots. Maybe zoom in a little bit more here. So these ones move to yellow, and then we'll move it back to green. After we do this, we're going to move the rest of these to red. Again, it looks like it could be another modulation direction, but it's actually a twin. Okay. Turn off the yellow. Put these somewhere. Gray is fine, I guess. And we'll move these to green. And we'll take a, yeah, so now you can see what twins look like in rlat in incommensurate mode. So disable incommensurate mode. And now we get a really good view of what a twin looks like, what satellite peaks look like, and what the sublattice looks like. So there's those twin reflections crossing. We've got our green sublattice and our gray superlattice or satellite peaks to correspond with this structure. Go back to unit cell. I'll just refine this really quick. The green group one final time. And yeah, so we're getting a really good cell parameters on the sublattice. So that's just one way of figuring out what's supposed to correspond to how to find a sublattice. That could take a lot of time going through different iterations of what I just did, but we figured it out eventually. And now I'm going to try to, the important step to not forget is to index the Q vector, which is our modulation direction in reciprocal space. So we'll go to incommensurate mode, and you'll see there's satellites, and there will be 1, 2, 3. You can index up to 3 modulation directions. This one only has 1. Let's turn off those red spots just to make it look nice. And incommensurate mode, zoom in. Okay. So if there were different, if there was more than one order of modulation, it would kind of look like the twinning did with extra rows of spots in different directions. So a 6-dimensional one would look kind of just like another lattice here in 3 dimensions, but we only have one which is going in this direction. So the way to index this is first, what we see here is 3 orders, so first, second, and third order satellites. So we'll select 3. And then we want to look down the direction that gives us unique information about the direction of the modulation. This isn't the best example. It looks like the modulation direction's almost exactly with the A-axis here, but it actually might be slightly misaligned. And with monoclinics, the best direction to look down would be the B-axis. Of course, that's a characteristic. That's the twofold axis for monoclinic. So we'll look down B star to index this. But basically, you're just looking for the direction where you can see any disparity between the sublattice and superlattice peaks. So we'll go select or measure incommensurate, and because we selected 3 orders, it'll give us 3 tick marks here, and we will just index. We will extend it out to here and index and set Q vector. So yeah, you can see it's very close to only the A-axis. Sometimes I've solved this structure and it's a little bit further than that, but we'll let the integration handle that. So it's now ready for integrating and then scaling. So now that we've set that. But integrating and scaling are different than a normal structure. So let's save this really quick. And yeah, reduce data and integrate images. And we're going to use this lattice, of course. Find runs. It's selected them. The only difference now is that we have to go to integration options, I believe, more options, and we have to change the maximum satellite index to 3, I believe. So that's all we have to do. And with that twin, we're just kind of ignoring those twin reflections. I've had issues in the past with trying to model twinning and modulation at the same time. It's kind of either or in Apex, but I think you're supposed to be able to. But I think there's some bug in the program, maybe, or I'm just doing it wrong. But I've tried. So what we're going to do is just ignore the twin domains and just try to focus on these reflections, even though the intensities of these may overlap with the twin domain, unfortunately. But we'll just ignore those and we'll just click Start Integration. Alright, so now that that's done, a few notes about this, about the collection, and about why I picked this crystal. As you saw, the spot shapes weren't the best. That can often be the case if it's like in this case it's a sheet silicate with disorder and twinning, and there's going to be issues with that. But that part isn't so important if it's finding the lattice, which it clearly did. I picked this structure because I'm used to it, but also it's a really good example of extreme modulation. We saw 3 orders of satellite peaks in this one, which isn't very common amongst modulated structures. Usually you only find 1 or 2, and so the modulation is just very clear. And the other thing is the satellite peaks were relatively intense relative to the sublattice. So that's not always going to be the case. It may even be difficult to, you may not even recognize that a structure is modulated until you use long exposure times and have a really good area detector, a modern area detector. I'm using kind of older equipment, and this was just a good example to demonstrate these things with. So that's why I used it. But yeah, if you're collecting on something you suspect is modulated, transmission electron microscopy, that can be very helpful, and run relatively long exposure times, because yeah, the sublattice peaks are going to be just much more intense than the satellite peaks, and it may drown them out. So it helps to have a high dynamic range on your detector. So just anything more modern would be very helpful. But anyway, so we're going to look at this and to make sure that we did it correctly. So we didn't forget to set the Q vector, which can happen. And so what you should see is this new section of the Q vector refinement. We have a really well fit lattice and a Q vector set on here. So that's the major difference from a normal crystal structure. So we know that we did things correctly here. And now we'll scale it. We can scale it at this step before going to JANA. And these are correct, but do not forget this part. You can kind of get away with not doing this, but this makes it much easier when you're starting out in JANA, is instead of output file type HKL file, we're going to use the HK6 for modulated structures, so it can just be directly read into JANA. There's other file types for dealing with twin structures, but we're not going to do that. And that's it. So we're just going to integrate like normal now, or scale like normal. And, it's not the best in the world. You may have to use this to indicate what Bravai lattice it probably is, go down in symmetry if you need to. In this case, I've done a lot of trial and error with this structure, and honestly, this is about as good as it gets, just because the structure is always going to be twinned. You can hardly get a crystallite that doesn't have a twin domain, and the overlapping reflections on the sublattice peaks create this discrepancy in the R internal. So we'll just have to deal with that. But this isn't that bad. It's just not as good as a normal like mineral structure would be. So we'll just deal with that. So not too bad. If I went down to triclinic, it would be better, but it would be inaccurate. This structure is probably not triclinic. This particular one is not triclinic, or it's just not very well described in that way. It's too close to being monoclinic statistically. So that's scaling. So other than just selecting the export as an HK6, it's not very different. So now that that's done, I'm just going to save it. You can do all the extras like getting the crystal dimensions and stuff before the scaling, but we're going to skip that for now and go directly into JANA 2006. It also would help if you have this. I like this plotter, MolCool QT. This is someone's homebrew program for plotting modulated structures, so you can, see the animations of them. It's a really good way of visualizing things as you go, because as for visualizing the periodicities and stuff, the only thing this has is these contours which is really helpful. But if you want to see the animations, you're going to need a separate program for that. So what we'll do is go File, New, Structure, New, and we got to find the directory. So usually that'll be your frames folder. And in my case, it's frames guest. And Antigorite3 was the one that we did. You're probably going to have to press escape. Just so that because this file has all the frames in it, so it's trying to read all those. But we just want to get to the work folder. And actually, it's probably a good idea just to move the folder out of there, or at least do this. We'll go to my frames folder, which is C frames guest and Antigorite. You want to at least create a copy of this. So that's the original solution, and we'll just work in this one, I guess, if we want. Relabel this original, and then we can just change things in this in case something goes wrong during the refinement. So we're in this directory, and we're looking for the green HKL file. Known diffractometer formats. This is a Bruker CCD. I don't know what the difference is there, but just make sure it's got the correct one. Yeah, 0M HKL. Next. Got the modulation vector, and all these should be correct if you're using conventional settings. This is the first kind of bug in the program, I think, where if you select twinning and try to do the twin matrices at this stage, it doesn't work. But I can show you what you would do later on is, after we do all this, you go to twinning and redo this. This one, I already know that the twin domain is around 001, and it's a 180-degree relationship between those domains. And then you just click up here and OK. And yes. And that's about all we can do with twinning, because I've had issues with trying to do twin modulated structures in Apex3. So anyway, we'll read those frames. And we already scaled it, so we can say none, finish, OK, yes, next. I leave a lot of these settings default. Oh, I never noticed introduced twin law. Maybe I should have done that. And yeah, JANA recognizes it as probably monoclinic, based on the lattice exceptions and stuff. Yep, C monoclinic. And yeah, so here we can't tell at this stage that it's not one of these three, but of course by default it'll select the highest symmetry one, another trial and error kind of thing. So we'll just go with that. And yeah, defaults, this is what you want to do. This is the I over sigma threshold. I just use the defaults. Default. And you can apply culling and all that, which I probably should have done, but it doesn't matter. So the formula for this, average formula, even though it's modulated, going to be Mg3 Si2O9H4. And we'll run our solution. And our starting point was an R of 32%, I guess. And after noise suppression, okay, well, that's a starting point. From here, you can work on it and follow the examples in the manual. I'll just accept that last solution. You know, you can refine it and read it in. There's a lot more to this after this stage, but you can open it in this program, for example. We'll just see what our initial solution was. It's going to be silly, but we can open that. Yeah, so this is going to be wrong, but close enough to start with. Let's see. This, oh god, okay, so we got BA like this, okay. So just as an example, I can tell just by these bond lengths, this is supposed to be magnesium instead of silicon. Those SIs are correct, and the modulation is going to be kind of messed up. Actually, that's pretty good. That's about what it should be, except there's a lot more work that this needs. But anyway, that's a start to how you get started with modulated structures. So I hope that was helpful.